Hello students, in this session we will be studying Biot Savart Law. We have studied that a current carrying wire produces magnetic field around it. Consider an arbitrarily shaped wire of length L. This wire is carrying current I through it. dl is the small length element of the wire. Let us first find the magnetic field denoted by dB produced by this small element dl at point P, which is at a distance of r bar from the length element dl of the wire. The magnetic field dB produced by the current I flowing through dl part of the wire at point P is given by Biot Savart law as dB is equal to mu naught divided by 4 pi I dl sin theta divided by r square, where mu naught divided by 4 pi is the constant, I is the current flowing through the small element dl of the wire, dl is the length of that small element, and r is the distance of point P from the length element dl. And theta is the angle between the direction of the length element dl and r bar. This is Biot Savart law. Multiplying and dividing this equation by r, we get dB is equal to mu naught divided by 4 pi I dl sin theta multiplied by r divided by r square multiplied by r. By making use of the definition of cross product, we can write dl r sin theta as dl bar cross r bar, and r square multiplied by r will be r cube. The direction of dB bar is dictated by the cross product dl bar cross r bar. So these two equations are known as Biot Savart law. The net magnetic field at point P can be obtained by integrating the magnetic fields dB bar from these small length elements. Now let us derive an expression for magnetic field due to current in a straight wire. Consider a wire which is infinitely long. Current I is flowing through the wire. We want to calculate the magnetic field B bar which is produced at point P, which is at a distance of capital R from the current carrying wire. Let us consider a length element of the wire, that is dl. Small r is the distance of this length element from point P. Theta is angle between dl bar and r bar. Then, according to Biot Savart law, the magnetic field produced by the length element dl of the wire at point P is given as dB is equal to mu naught divided by 4 pi I dl sin theta divided by r square. Here the direction of dB bar is given by cross product dl bar cross r bar. Hence, it will be into the plane. Now let us first calculate the magnetic field at point P by all the current carrying length element in the upper half of the infinitely long wire. This can be obtained by integrating the equation for dB from 0 to infinity. Also, we calculate the magnitude of magnetic field produced at point P by the current carrying length element in the lower half of the wire. By symmetry, this magnitude is same as that of the upper half of the wire. The direction of this field is also same as from the upper half of the wire. That is, it is also going into the plane. Adding both the contributions, that is magnetic field due to upper half of the wire and lower half of the wire, the total magnetic field at point P is given as B is equal to 2 times integration of dB from 0 to infinity. Substituting this formula for dB in this equation, we get B is equal to 2 times mu naught divided by 4 pi. Since mu naught divided by 4 pi is constant, it will come out of the integration sign. So we get B is equal to 2 mu naught divided by 4 pi integration of 0 to infinity I dl sine theta divided by r square. By using Pythagoras theorem for this triangle, we get small r square is equal to L square plus capital R square. So r will be equal to square root of L square plus capital R square. This angle is theta. So this angle over here will be pi minus theta. And we know that sine theta is equal to sine pi minus theta. From the diagram, sine pi minus theta will be equal to opposite side divided by hypotenuse. So sine pi minus theta will be equal to opposite side, that is capital R, divided by hypotenuse of this triangle, that is small r. So sine pi minus theta will be equal to capital R divided by small r. Let us substitute the formula for small r as square root of L square plus R square. So sine theta will be equal to r divided by square root of L square plus R square. In this formula for B, let us substitute sine theta is equal to r divided by square root of L square plus R square, and small r square is equal to L square plus R square. Also in this formula, 2 will get cancelled out. B is equal to mu naught I divided by 2 pi integration 0 to infinity. Instead of sine theta, we have substituted it as r divided by L square plus R square, and instead of R square, we have substituted it as L square plus capital R square multiplied by dl. The denominator, that is square root of L square plus R square multiplied by L square plus R square, can be written as L square plus R square the whole raised to 3 by 2. By solving the integration part, that is integration of 0 to infinity dl divided by L square plus R square the whole raised to 3 by 2, we get it as equal to 1 divided by R square. So instead of integration, let us substitute it as 1 divided by R square. Capital R over here has come out of integration sign as it is constant. So we get B is equal to mu naught I divided by 2 pi R multiplied by 1 divided by R square, which will be equal to mu naught I divided by 2 pi R. So this is the formula for magnetic field produced at point P due to infinitely long straight wire. Now let us study about force of attraction between two parallel wires. Let us consider two wires which are placed parallel, and current I1 is flowing through the first wire and current I2 is flowing through the second wire in the same direction as the first wire. Both the wires are placed at a distance of d from each other. Consider section of length L of both the wires. The magnetic field produced due to the current I1 flowing through the first wire is given as B1 is equal to mu naught I1 divided by 2 pi d. We have derived this expression in the previous slide. We now apply Lorentz force law to find the force on wire 2 which is carrying current I2, and it is placed in the magnetic field B1 produced by the first wire, and it is given as F21, that is force on the second wire, which is placed in the magnetic field produced by the first wire, is equal to I2, that is current flowing through the second wire, multiplied by B1, that is magnetic field produced by the first wire, multiplied by L, that is length of the second wire. Let us substitute the formula for B1 in this expression. We get F21 is equal to I2 mu naught I1 divided by 2 pi d, the whole multiplied by L. By rearranging the terms, we get F21 is equal to mu naught I1 I2 L divided by 2 pi d. And force per unit length on the second wire, which is placed in the magnetic field produced by the first wire, will be equal to F divided by L, which is equal to mu naught I1 I2 divided by 2 pi d. The direction of this force on wire 2 will be towards wire 1. Now let us apply Lorentz force law to find the force on wire 1 carrying current I1, and it is placed in the magnetic field B2 produced by wire 2. So we get force on wire 1, which is placed in the magnetic field produced by wire 2, is equal to I1 multiplied by B2 multiplied by L, where I1 is the current flowing through the first wire, B2 is the magnetic field produced by the second wire, and L is the length of the first wire. The magnetic field produced by the second wire, that is B2, is equal to mu naught I2 divided by 2 pi d. Let us substitute this formula for B2 in this expression. We get F12 is equal to mu naught I1 I2 multiplied by L divided by 2 pi d. Force per unit length on the first wire will be equal to F divided by L, which will be equal to mu naught I1 I2 divided by 2 pi d. This force on wire 1 is directed towards wire 2. So we see that both the wires experiences same amount of force towards each other. So they will be attracted towards each other. And when the current flowing through these wires is anti-parallel, the wires will repel each other. So in this session, we have studied Biot Savart law. We have also derived an expression for magnetic field and force on a straight current carrying wire using Biot Savart law.